Everyone. Today we're going to get started with talking about inequalities. Inequalities, and I'm sure you've seen these before, but inequalities are statements where you're saying that two numbers are not equal to each other, hence the word inequality. And if they're not equal to each other, there's really two choices. Either the number is bigger than the other one or it's smaller than the other one. So this is where we're talking about greater than and less than. Before we get started, I do want to point out that at this point in the game, it's really important that you can tell the difference between the greater than and less than sign without relying on like the elementary strategy of, oh, you're always going to eat the bigger number or whatever it happens to be. Because a lot of the times here you're going to be working with variables, not numbers. And so you can't look at two numbers and know which one is bigger if they're not actually giving you a numerical value. So this is the less than symbol. This is the greater than symbol. And if you need a way to help you remember this, if you look at the less than symbol, if you picture kind of unfolding it, grabbing the two edges and kind of pulling them apart, this one makes a letter L for less than. This one would make a backwards L. But so the less than symbol is this one. The greater than symbol is this one. Okay, so onward here. First, we're going to just talk about how to display these values on a number line. And you may have done this before. But if I want to show all of the x values that are greater than 4, everything that's larger than 4, that would be everything to the right of 4 on the number line. I know my line got cut off a little bit, but yours should look okay. Here's how we handle this. We want to somehow show that we're starting at the number 4. But because I only want things that are larger than 4, I don't actually want to include 4 in my answer. So I'm going to use an open circle on the 4, and then I'm going to shade in everything to the right, because on a number line, everything to the right is greater than. And I'm just going to make a darker arrow here to show that that keeps going. So any number in this shaded area counts as part of the solution to this inequality. Okay? Now, you'll also see inequalities with this line underneath. And again, you've probably seen this before. That's an equal to bar. So this means that x is either less than or equal to -2. So the big difference here between this one and this one is that in this case, we do actually want to include the -2 as a possibility. And so what I'm going to do this time is I'm going to put a closed circle or like a filled in dot on the -2. And then I'm going to shade everywhere less than, which on a number line is everywhere to the left. Okay. So for the most part, as far as which direction to shade, you can trust the inequality symbols. If this is pointing to the left, then you're shading to the left. As long as the variable is as long as your statement starts with the variable. So x is greater than this. But if I rewrote this as, for example, 4 is less than x, okay, which is really saying the same thing, you want to make sure you're reading from the perspective of x. So this is still saying x must be larger than 4, okay? So you have to be a little bit careful with inequalities. It's not as easy as equal signs where it doesn't matter if you flip the things around. Okay, so let's talk about some more complicated ones, okay? These are ones that are set up almost like equations, and we have to solve them before we put the solution over here. So if I want to shade everywhere on the number line where this statement is true, I need to boil this down to just a statement about x, like the 2 we had up above here. So I'm going to solve this just like an equation. I'm going to say +1 + 1, okay? And that leaves me with 2x is less than 6. And then I'm going to divide by 2 and divide by 2. And I end up with x is less than 3. Okay, if I want to check that, and I'm going to check it in a calculator just so you can see what I'm doing here, although you probably could do this in your head just fine. To check to make sure this statement is true, I need to pick a number that is smaller than 3. So let's pick maybe 1, okay? Just anything that's smaller than 3, and I'm going to plug it into this 2x minus 1 and make sure that it comes out to be something smaller than 5, because that's what this statement says. So 2 times 1 minus 1, and I want to know, is that smaller than 5? Yes, it is. Okay, so this checks out. This is correct. And so I'm going to use an open circle because there's no equal bar here. And I'm going to shade everything. And I know it seems weird that I'm moving in this direction, but as a right-handed person, it's easier to shade this way. Everything to the left of that open circle. Okay, and so that means if I picked any number in this shaded area or any number that's further to the left here and plugged it in, this statement would hold up to be true. If I picked a number over here like 5, 2 times 5 minus 1 would not give me something that's less than 5. Okay, but anything lower than 3 would make this sentence true. Okay, so let's look at the next one, and I will warn you ahead of time, there's something a little weird that happens here, but we're going to kind of plow through it the same way, and then I want to point out what happens. So I would probably start by subtracting 1 on each side, and so I end up with negative 3x less than or equal to 6, and then let's divide by negative 3, and I end up with x is less than or equal to negative 2. Okay, so I'm going to pick something that is less than or equal to negative 2. So I'm going to pick negative 5, because if I'm at negative 2, something less than negative 2 would be negative 5. And I'm going to plug in negative 5 to this statement. So 1 minus 3 times negative 5 gives me 16, which is not less than 7. Okay. But watch this, if I pick something on the other side of negative 2, if I pick something that's actually larger than negative 2, so let's say positive 3, okay? If I do 1 minus 3 times 3, I end up with something that is smaller than negative 7. All right, so something got switched around here, right? This is not correct. This statement needs to read the other way. The reason for this comes up in this step right here. When you divide by a negative, if you think about dividing by a negative, you're flipping from one side of the number line to the other, right? Dividing by a negative takes you from positive land over to negative land. Or if it's a negative number and you divide by a negative, it flips you back to positive land. Either way, the numbers run in the opposite direction when you're looking at positives versus negatives. And so when you make that flip from one end of the number line to the other, your inequality needs to flip as well. That's going to happen every single time you divide by a negative number. So when this happens, okay, the inequality here is going to flip in the other direction. It's going to be a greater than or equal to negative 2. You have to remember to do that. And if you are worried that you'll forget, get in the habit of checking your answers like we've been doing here. So I want to do a closed circle on negative 2, and I want to show that actually these numbers are all of the ones that make the sentence true, even though the original equation had a less than in it. Okay, because of that negative, because of dividing by a negative, this flip around happened. Okay, technically that also happens if you divide or if you multiply by a negative. So multiplying and dividing by a negative is what makes this occur. The dividing by a negative is way more common. Okay, we'll be practicing a few more of those today. Let's jump into a new concept here. And maybe not new. I think you've seen this before. But we are going to be using phrases that involve unions and intersections in the next set of examples. So just to remind you, a union is the set of, I'm going to say objects, although we know in math usually our objects are numbers that belong to group A or group B. And then I'm just going to throw in here, if they happen to be in both group A and group B, they're also included in the union. Okay? Let me go ahead and give you the definition for intersection. And of course, if you need to pause to write these down, you can. And then we'll kind of compare and contrast them and talk about the difference. Intersection is the set of objects that belong to group A and group B. So you will notice those definitions are awfully similar to each other. Here's the key difference. This definition uses the word or. This definition uses the word and. Okay? So or goes with the union, and goes with the intersection. And so here's the difference. Let's suppose I am going to throw a party for the union of my classes and Mrs. Westvere's classes. Okay? I think there's probably at least some of you that have Mrs. Westvere as a teacher. So if I'm throwing a party for the union, that includes everybody in all of my classes and everybody in all of her classes. And if you happen to be in both, if you happen to have both teachers, great, you get to come to the party too. Okay? But if I throw a party for the intersection, the only people who get to come are the people who are in both of our classes. So if you have me as a teacher, but you don't have her, sorry, you don't get to be invited. Okay? That's what the intersection is. So the intersection is a smaller group than the union. The union includes everybody in either one of the groups. The intersection only includes the overlap between the two. I'm going to throw in some symbols here. The union, we use this symbol that looks like a letter U. Okay, that's the symbol for union. Intersection is that same symbol flipped upside down. So this is the symbol for intersection. And if you're looking at the Venn diagram here, if this first circle represents group A and the second circle represents group B, this area here in the middle represents the intersection. Okay, so these are the things that are in both groups at the same time. And if I put everything in both circles together, that represents the union. Okay, so the union is, in a lot of contexts, easier to work with because we don't have to worry about leaving anybody out, right? We just take this whole group and this whole group and throw them in together, right? The intersection, we have to do some work to verify. So if I was, again, let's go back to my party analogy. If I was throwing a party for the union, it'd be really easy to just list off a bunch of invitations to everyone in my classes and everyone in her classes. But for the intersection, I would have to do some work, right, to verify who's in both classes. And that's what you're going to see mathematically, too, is when we do problems involving the intersection, it takes a little bit more work mathematically to figure out which numbers it should include. Okay, so let's go on to those examples here. So what we're working with now are inequalities with those union intersection words to them, okay? So I want you to notice that this one uses the word and this one uses the word or, which means that this one is an intersection. This one is a union. Okay? So when I'm trying to find all of the numbers that are greater than or equal to -2 and less than 4 at the same time, I can't just start shading things in on the number line because I have to make sure they fit in both groups. So anytime I'm working with an intersection, what I typically do is do my initial shading up above the number line. So greater than or equal to -2 is going to look like this. It's going to be a closed circle on -2. Okay, actually, I'm sorry. I'm going to do this in red so you can see kind of what my sketch is versus what my final answer would look like. So this would be closed circle and shade everywhere to the right. And then x is less than 4 would be an open circle on 4 and shade everywhere to the left. So what I actually want to put down as my final answer is only the numbers that are in both groups. So you see the overlap between the two lines. So I'm going to go straight between these, the places that are double shaded. Oh, that's supposed to be over the 4. Sorry about that. I'm going to do a closed circle here on the -2. Going to do an open circle here on the 4, and I'm going to shade everything that's in between. Okay? And so this right here would be my final answer. When I'm looking at your responses to these, I will always be looking at what's on the actual number line as your final answer. Now, for some of you like to do all of your shading up above the number line. Okay, that's okay. However, if you're going to have a bunch of different shading up here above, make sure that I know for sure which one is your final answer. Okay, so here's the thing with this next one, though. If I'm doing a union, everybody gets invited to the party. I don't have to worry about excluding these numbers or excluding these numbers, right? So when I'm working with an or, I'm just going to put both things on the number line at the same time and see what happens. So greater than or equal to -2 would be all of these. Less than 4 would be all of these. Now, I'm technically putting an open circle there, but 4 is already getting invited to the party because it's part of this group, right? So the open circle in that case doesn't really matter. And I'm shading everywhere to the left. And so you'll notice in this case, everything gets shaded, okay? In this case, really the solution set is all real numbers. Every number falls into one of these two categories. Not everything falls in the intersection, but everything falls in the union of those two categories. Okay? That doesn't always happen with unions, by the way. Okay, take a look at this notation. And I think the sooner you wrap your head around what this is really saying, the easier life is going to be for you mathematically. This is an interval notation. It is also a condensed version of writing an intersection, okay? So really what this is saying is, if you read it from the perspective of x, this is saying x is larger than 3 and x is less than 5. But they've kind of done the hard work for you. By smashing it together like this, it shows you where x lives. X lives between 3 and 5. So I can just jump straight to shading that, kind of like I did up here. So I'm going to do an open circle on both. So an open circle on 3, open circle on 5, shade everything in between. Okay, and I could graph these separately like I did before, but this is going to be the overlap. So whenever something is written like this in math, it's really talking about all the numbers that are between these two values. Okay, so now we get into some crazy notation. And this notation, by the way, is known as set builder notation. We're not going to be doing a whole lot with this notation this year, but you will see it more and more the higher up you go in math. You can ignore a lot of it, though, because it's just there for notation purposes. This is really saying all x's such that x is larger than 2. This is what I want you to focus in on. X is greater than 2. This is a union symbol, so this is going to be an or. And then x is less than or equal to -3. Remember, when it's a union, everyone gets invited to the party. So you can just put both things on the number line and see what happens. So greater than 2 would be open circle, shade to the right. Less than or equal to -3 would be closed circle and shade to the left. So this time, not everything gets invited to the party, but you kind of get the two ends of the number line shaded in. I would actually say this type of answer is more common than this type of answer, but it can happen either way. I mean, if there's overlap there, you're going to get something more like this. Okay, my next one, just to kind of catch your attention here, this is an intersection, right? And I guess I should have said this is a union. And this is an and. Okay, so this is one of the ones where I have to be concerned about overlap. And again here, I'm focusing in just on the inequality pieces. So this is saying that x is between -1 and 3. Okay, I'm going to go ahead and shade that above the number line so I can look for overlap. So -1 is getting a closed circle because of that equal bar. 3 is getting an open circle and shading everywhere in between. So this right here is really this inequality, okay? I need to know, where does this intersect with everything greater than or equal to 1? So greater than or equal to 1 would be this and everywhere to the right. So what I want to look for now, as far as my final answer, is the intersection. What do they have in common? And that would be everything from +1 to +3. With a closed circle on 1 and an open circle on 3. And so these numbers here would be my final answer. Okay, that's really it for section 5.1. Looking at, these are called compound inequalities, when you're working with more than one inequality at the same time and you have to decide, is it an and or an or situation. Okay, you're also going to be working with some solving inequalities in this lesson. So good luck to you, and I will see you next time in class.